Hey everyone, welcome back. This is part 3 of our math theme problems you should know how to do series. Today we'll be looking at the infamous handshake problem, as well as how it relates to the number of diagonals in a polygon. So, without further ado, let's get into it. Let's start with a brief overview of the handshake problem. We have an integer n people in a room. Each goes around and shakes everyone else's hand exactly once. How many handshakes total occur? Seems pretty straightforward. If you'd like to try it for yourself, pause the video now. Otherwise, let's keep going. So why is this problem so common? And why is it so tricky? You would think you could just count them, which is easy with a small number like 5, but it gets harder as you get to 20 or so people. The reason this problem is so common is because it's many people's first exposure to the subset of math called combinatorics. Combinatorics is defined as the branch of mathematics dealing with combinations of objects belonging to a finite set in accordance with certain constraints such as those of graph theory. This is just a fancy way of saying counting stuff, but with math. So let's try it. Let's assume our integer n is 5. We have 5 people in the room. Your first thought might be to do 5 times 5. 5 people, it's 5 handshakes a person, so 5 times 5 handshakes a person gives us the total handshakes, right? You quickly should realize something is wrong here. Look at the boxes going diagonally from the top left to the bottom right. In each one, people are shaking hands with themselves. That doesn't work out. Turns out there are only 4 people in the room that each person can shake hands with, accounting for themselves, being one of the 5. So let's try 5 times 4. Now we don't have this self-shaking problem, but we do have another problem. I don't know if you've noticed, but these two handshakes are really the same. So let's get rid of one of them. Turns out every single handshake here has a second, equivalent handshake. Why? What we failed to account for is that once you've shaken someone's hand, they've also shaken yours. So we've double counted each handshake. So how can we generalize this? First, let's write out our experiment and its result. We had 5 people, each shaking everyone else's hands once, and we counted the total handshakes. So we started with 5 people, and we noticed 2 important details. First, you can't shake your own hand. So we multiplied our 5 people by 4 people, by the 4 other people in the room. Then we realized that a handshake from A to B is the same as a handshake from B to A. Once you've shaken someone's hand, they've also shaken yours. So we divided by 2 to account for the fact that every handshake had been double counted to get a total of 10. I want to change one thing before we make this a formula. Why 4? Because 1 less than 5, I mean, obviously. Because we just took each person out of their own handshaking lineup. So there were 5 people in the room, but if you're in the perspective of one of those people, there are 4 other people in the room. So I'm going to change this to 5 minus 1. You'll see why that's important in a second. Now let's try to generalize for any room with n people. Instead of starting with 5, we can start with n, multiply by n minus 1 other people in the room, and we've still double counted, so we still divide by 2. And there we go. We have h, our number of handshakes. If that was a big logical leap, try to go back in the video and track where we get each operation from. Then try to think about how that would manifest in a room with 6 people, or 7. If you're ready for another challenge, let's keep going. This is another variation on the same problem, though it might not look like it. In terms of n, how many diagonals does a concave n-gon have? An n-gon is just a polygon with n sides. The diagonals are line segments drawn between non-adjacent vertices. The first 4 sets in the pattern are shown here. I would not recommend trying to draw subsequent variations. Counting them gets to be quite difficult. If you'd like to try to solve it on your own, think about how you can modify the previous problem to solve this one, and pause the video here. If you're ready for the solution, here we go. At first you might be wondering, wait, how is this related? Let's imagine 4 people sitting around a table. We can draw a concave quadrilateral connecting them. The diagonals of this quadrilateral can be represented by handshakes to non-adjacent people, right? Similarly, if we think of 8 people around a table, we can imagine an octagon connecting them. And again, diagonals can be drawn from each vertice to all non-adjacent vertices. If you think you might have a sense of what to do now, pause the video. If you've already solved it and want to check or if you're still feeling lost, let's keep going. Let's imagine a heptagon. Let's pretend we're standing at a given vertex. and we need to shake hands with all non-adjacent people. Here's the key. We now cannot shake hands with ourselves, obviously, but we also can't shake hands with either of the people next to us, leaving 4 handshakes for me. Now how can we adapt that formula we developed for the original handshake problem to calculate for this one? In the original, there was only one person we couldn't shake hands with, ourselves, so we subtracted 1. In this case, there are 3 people we can't shake hands with, ourselves and the 2 people next to us. So if we change that 1 to a 3, turns out the rest of the formula is still applicable. We still count that many per vertex, and we've still double counted each one, so we still divide by 2. The final formula for diagonals looks a lot like the one for handshakes, n times the quantity n minus 3 divided by 2, giving us the diagonals. So what can we take away from this set of problems and solutions? Number 1, counting problems are often just a game of figuring out what factors are going to affect the result, and then appropriately developing a formula that accounts for all those factors. Number 2, if a problem is asking you to generalize, start with a specific question. Plug in a value, try to develop some strategies or an equation, and then generalize once you have a deeper understanding of the problem. It can be quite hard to imagine a room of n people, but a room of 5 people starts to make a little more sense. Number 3, if you get a wrong answer, instead of scrapping your strategy, look for ways to modify it to account for some factor you hadn't considered. In the handshake problem, we modified it twice to account for shaking our own hand and double counting each handshake. Lastly, and this is why I showed 2 similar problems, if a problem seems daunting, try to see how it might be related to a problem that you know how to solve, or rewrite it in a more understandable way. That's all for this video. Check back in later. Our next video is on the power of the point, which is a super useful tool for calculating lengths of lines drawn in and around circles. Till then, peace out, math people.